All right, ladies, this is theorem 4.2.1. Oh, hi, by the way. I don't think I said that. This is section 4.2, probably part 1 of 2 videos for the fall 2018 semester, because I think I may have a video from previously, but I wanted to redo that video. And so let's get into it. This will probably be broken up into 2 videos, and I think I just said that. So let's continue. All right, so let's look at this theorem here. Theorem 4.2.1, which says let A, B, and C be sets in F. Maps from A to B, G maps from B to C. Then G composed with F is a function from A to C, and the domain of G composed with F is equal to A. So we're actually going to prove this. Now, what I would suggest, because I wrote it out to save time, is that you pause the video and write this out and then come back and go over the video with me. Okay, so recall from section 3.1, we know, and I don't know if we did this directly, but in section 3.1, we know that G composed with F is a relation from A to C. So we have to show the 2 conditions that we talked about in class in terms of showing a relation is a function, and that's showing that the domain is equal. In this case, it would be, since it's G composed with F, it's going to be A, right? And showing that if you take 2 elements of, there's 2 values in your domain, and if they map to the 2, let's say X, Y. So in the show part right here, if X, Y belongs to G composed with F and X, Z belongs to G composed with F, then Y has to equal Z. Otherwise, it's not a function. So you may realize, or maybe, I don't know if you realized from doing the homework, that it's simpler to prove that second condition, right? And so that's why we're starting. We have to prove both, but I just want to start with the second condition since it's simpler to prove. So we suppose our if statement, that's there from our show part. Then what that means is this. If X, Y belongs to G composed with F, by definition, that means there exists some S, or you can call it whatever variable you want, such that XS belongs to F and SY belongs to G. Okay, and that's because that's from the definition of composition. Also, since we said suppose that XZ belongs to G composed with F, that means there's a T, because we can't assume that they're the same letters, but there's a T belonging to B such that XT belongs to F and TZ belongs to G. Well, we know that F is a function, right? And if we know that F is a function, then we can conclude that X, and since XS belongs to F and XT belongs to F, then we can conclude that S has to equal T. Otherwise, it wouldn't be a function, because now we're talking about F by itself, not with the composition. And so therefore, since S equals T, then we can conclude Y equals Z. Now you may have to, your notes are probably on one page, right? And mine is going to a different slide, but make sure you understand why that's true. It should be clear, but if not, go back over it. And if you still have questions, you can speak with me on Monday about it. Okay. All right. So now we have to show that the domain of G cross F is equal to A. Okay. So again, in section 3.1, although I don't know if we did this directly, I feel like we talked about composition in 3.1, but we may not have done this directly. But we also have the fact that the domain of G composed with F is a subset of the domain of F, which is equal to A. So remember, since the domain of G, to show that the domain of G cross F is equal to A, you show that they're subsets of each other, right? You show that one is a subset of the other, so that the domain of, oh, that marker is not good. You probably can't see that. But the domain, and you really don't have to write this down. You can if you want to extend your show part. So the domain of G composed with F is a subset of A, and A is a subset of the domain of G composed with F, not cross. All right. So if you want to extend your show part to that, you can. All right. So we proved that. So we know that fact by previous theorem. So now we just need to show that A is a subset of the domain of G composed with F. We'll let little a belong to the set A. since A is equal to the domain of F, that means there exists a B such that AB belongs to F, right? If we're saying A is an A and it's a function, then it has to be, it's well defined. So since B is equal to the domain of G, right, there exists a C such that BC belongs to G. Then by definition, AC has to belong to G composed with F. And therefore, A is belongs to the domain of G cross F. So again, sort of process this, take it step by step, see if this makes sense. And if not, ask me questions on Monday. All right, ladies. So now let's just make a quick note, because now we can simplify our notation a little bit. So we know F goes from A to B and G goes from B to C. And so Y is equal to F of X and Z is equal to G of Y. We can rewrite them. We can look at our functions as Y equals F of X and Z equals G of Y, right? So G composed with F of X is, we can now use this simplified notation, which you probably remember from pre-calc. And visually, I just want to make sure we're clear on what's going on. So F goes from A to B, right? So this is A and B, and so F is mapping that. Then from B to C, you have your G, okay? And then your composition of G composed with F, because you do your F first and then your G, is going to be A goes to C, right? And so I just want to make sure sort of that's clear when we look at it visually. All right, I want to mention this theorem. You can look in the book to see how they proved it, but I just want you to know that you have this theorem. So A, B, and C and D are sets. F goes from A to B, G goes from B to C, and H goes from C to D. And this is just the associative property. So if you have the in parentheses H composed with G composed and then composed with F, that's the same as H being composed with G composed with F. So this just says associativity holds under composition of functions. Commutivity does not hold. Okay. All right. So let's look at theorem 4.23. And this theorem says F, it's just dealing with F actually. So let's say F is a function that goes from A to B. Then F composed with I sub A is equal to F. And I sub B composed with F is equal to F. Now, you should remember, hopefully you remember, we talked about this. And so recall I sub A, I should put, of X, what maps from A to A, and it's given by the function I sub A of X equals X. All right, so it's another way to look at your identity. It's the identity function ideally, and that's why the I is there to represent the identity. Okay, so that means if you have I sub B of X, then it's going to map B to B. And so that's going to be I sub B of X equals X. All right. And so we have to prove, and this proof is going to be sort of set up a little differently, but hopefully you understand the reasoning behind it. And so here, visually, let's see if we understand what's going on. So we're just looking at the first part, because the second part I'm going to leave as an exercise for you all. But looking at that first part of the theorem, F composed with I sub A equals F. So let's see if visually we can understand what's going on. So let's visually look at F composed with IA. All right, well, since this is our inner function, right, we're starting there, and the domain and codomain are actually the same, right? So that's mapping that. And then F goes from A to B. And so we know our final result is going to be like this. However, what this is saying, I want to be careful to make sure I explain it. Hopefully you guys understand. But what this is saying is that if I input a value here, right? Well, it has to come from set A. And since whatever that value is, the identity function maps it out, or it gives you back that value. So that means the codomain is A, right? Which happens to be the range in this case. They're going to be the same. And so then you take that value and plug it into an F it. You guys like that? And then you get out B. Well, what this is saying is that f composed with I of A is just the same thing as f of x, right? And it really is. It's just the same thing as saying f of x. And so that's what we have to prove. Visually, hopefully that made sense. If not, we can talk about it. But that's what this is saying. And so in terms of the proof, we have, it's actually a short proof, but it's a little different because you would think, oh, we have to prove that they're subsets of each other. And that can get complicated. So what we have to, basically another way, whenever we have functions, if we can show that their inputs will be the same and their outputs will be the same, then they're the same functions, right? Because if you have two functions and they all have the same inputs and they all give you the same outputs and the same, and when I say that, I mean, if I input a value that in one function, if I input that same value in another function and I get the same outputs, then they're the same functions, right? So that's what we are concluding here. Okay, so let's look at this. So one thing that we have is that the domain of f composed with I sub A, we just showed in theorem 4.2.1, we just showed that equals the domain of IA. Well, the domain of IA, since it's the identity mapping itself to itself, that's just equal A. Well, that's the same as the domain of F. So we just showed the domain of the left-hand side here is equal to the domain of the right-hand side. Well, the next thing is to show that their outputs are the same. And so that's actually easy to show too. So if we let X belong to A and then compose the left-hand side, well, F composed with I sub A of X, that's equal to this, right? Because that's our new notation. Well, we know that I sub A of X gives us back F. So that's just equal to F of X. So we just showed that the domains will be the same and the ranges, the outputs will be the same. And so therefore we can conclude that F composed with I sub A equals F. Okay. And again, this is since the inputs and outputs. Oh, can I spell outputs? That is horrible. Outputs are the same. All right. So I want you to try that so try to prove that second part, that I sub B composed with F is equal to F. And if you turn that in on Monday at the beginning of class, I'm not even going to ask you for it. Just hand it in to me. I'm not going to ask, did anyone do it? Just hand it in to me, and that'll be worth a half a point on the next quiz that we take. Okay, so here's another theorem, and I want you to think about this and try to and write down the proof in your book. I'm not going to go over in this video, but of course, if you have questions, we can go over it on Monday. So let F, I'm just going to read it. Let F be a function from A to B with the range of F equaling C, right? Because this is really the codomain, right? If F inverse is a function, then F inverse composed with F equals I sub A, and F inverse and F composed with F inverse equals I sub C. Okay, so a subset, here's just a note, a subset of a function is still a function, okay? Thus, to create another function, if you remove some of the ordered pairs from a given function, you still have a function, all right? And this is what's known as a restriction. All right, so I actually think I'm going to stop this video, so I'll end part 1 of this video, and then the next video, I'm going to finish up this section, talk about restrictions, and do some examples as well.